Welcome back to Boring Science for Sleep, where the most fascinating mysteries of the universe become your gentle companions into rest. I'm so glad you've chosen to spend this quiet time exploring the cosmos with me tonight. Before we begin our journey into one of the most mind-bending questions in all of science, I'd love to hear from you. When you look up at the night sky on a clear evening, what do you imagine lies beyond the farthest star you can see? Is there an end to it all? Or does space simply stretch on forever? Share your thoughts in the comments below. I find that our intuitions about infinity are often beautifully different from one another. Tonight, we're going to explore a question that has puzzled humanity's greatest minds for centuries. Can the universe be infinite and still have an edge? It's a question that seems contradictory at first, like asking whether a circle can have corners or whether silence can have a sound. Yet as we'll discover together, the universe has a way of being far more elegant and surprising than our earthbound experience might suggest. So find your most comfortable position. Let your breathing slow and deepen, and imagine yourself floating weightlessly in the vast star-filled darkness of space. The temperature here is just above absolute zero, cold beyond earthly experience, yet somehow in our imagination we feel perfectly warm and safe. Around us, ancient starlight travels billions of years to reach our eyes, carrying stories from the very edges of what we can observe. Tonight, we'll follow that light on a gentle journey toward understanding one of the most beautiful paradoxes in all of science. Picture, if you will, a summer evening in the countryside far from any city lights. The Milky Way stretches overhead like a river of faint silver dust, and you're lying on your back in soft grass that still holds the warmth of the day. The air smells of a night blooming jasmine, and somewhere in the distance you can hear the gentle sound of water moving over stones. This is how humans have always encountered the universe, as observers looking outward from our small warm world into something vast and mysterious. For thousands of years, people have gazed up at those same stars and wondered about the nature of space itself. Does it go on forever? And if it does, how can we speak of it having boundaries or edges? The ancient Greeks were among the first to seriously grapple with this question. Imagine Archimedes, perhaps, walking along the shores of Sicily as gentle waves lapped at his feet. He understood that the earth was round, not flat as it appeared, and he began to wonder whether space itself might have similar hidden properties. Could something be both finite and infinite at the same time? What Archimedes and his contemporaries couldn't have known is that they were touching on one of the deepest questions in modern cosmology. The universe, as we understand it today, is far stranger and more wonderful than an ancient philosopher could have imagined. It's a place where time itself can stretch and compress, where space can curve like the surface of a soap bubble, and where the very concepts of edge and center take on meanings that our everyday experience could never prepare us for. As we prepare to explore these ideas together, imagine the gentle sound of your own heartbeat, steady and rhythmic, like a cosmic clock marking time in the vast silence. Each beat represents not just a moment in your own life, but a moment in the life of the universe itself, a universe that may be infinite in extent, yet still possess something we might call a boundary. To understand how the universe can be both infinite and bounded, we need to begin with a simple but profound realization. The universe is not just a container filled with stars and galaxies. The universe is space and time themselves, woven together into what Einstein called spacetime. expanding and evolving according to laws we're only beginning to understand. Imagine you're holding a deflated balloon in your hands. The rubber is soft and pliable, and you can see that it has a definite surface, a boundary that separates the inside from the outside. Now slowly begin to inflate the balloon. As air fills it, the surface stretches and grows, but it never loses its essential character as a boundary. Every point on the balloon's surface is still part of that boundary, even as the boundary itself expands. This is our first glimpse into how something can be finite yet still grow without limit. The balloon's surface has a definite area at any given moment, yet as we inflate it, that area increases continuously. If we could inflate it forever, the surface would grow infinitely large, yet at any snapshot in time, it would still be finite. The universe behaves in a remarkably similar way, though with an added dimension of complexity that makes it even more beautiful. Like the balloon's surface, space itself is expanding, but unlike the balloon, which expands into the air around it, space expands into nothing at all. Or rather, it creates room for itself as it grows. Picture yourself floating in a vast ocean on a perfectly calm night. The water is so still it's like a mirror, reflecting the stars above so perfectly that you can't tell where the sky ends and the water begins. Now imagine that this ocean is growing, not just spreading outward, but creating new water, new ocean with every passing moment. The horizon around you moves farther and farther away, yet you remain floating in the same gentle spot, feeling the same warm currents, breathing the same salt-scented air. This expansion happens so gradually and on such an enormous scale that we don't feel it in our daily lives. The space between Earth and the Sun isn't stretching. Gravity holds our solar system together too tightly for that. Even the space between our galaxy and nearby galaxies remains relatively stable. It's only at the largest scales, between galaxy clusters separated by hundreds of millions of light years, that we can observe this cosmic expansion directly. The light from distant galaxies reaches us stretched and reddened, like the sound of a train whistle dropping in pitch as the train moves away from us. This redshift, as astronomers call it, is our primary evidence that space itself is expanding. The farther away a galaxy is from us, the more its light is stretched, and the faster it appears to be moving away. But here's where the story becomes truly remarkable. This expansion doesn't have a center. There's no point in space from which everything else is moving away. Instead, every point in the universe sees itself as the center of the expansion, with everything else moving away from it. It's as if the universe is inflating like our balloon, but we live on the surface of that balloon, unable to see the larger structure from outside. In the early decades of the 20th century, a quiet revolution was taking place in our understanding of the cosmos. Edwin Hubble, working with the massive telescopes at Mount Wilson Observatory in California, was making observations that would forever change how we think about space and time. Picture Hubble on those clear, cold nights at the mountains above Los Angeles, the city lights still dim enough that the Milky Way blazed overhead in all its glory. Through his telescope he could see spiral nebula, what we now know to be distant galaxies scattered across the sky like faint smudges of light. With painstaking care he measured the light from these distant islands of stars, discovering that almost all of them were moving away from us. But Hubble's most profound discovery was that the farther away these galaxies were, the faster they were receding. This wasn't the random motion of objects flying apart after some cosmic explosion. This was something far more systematic and beautiful, the expansion of space itself. Imagine standing in a vast field during a gentle snowfall. Each snowflake that falls represents a galaxy, and as the snow continues to fall, the snowflakes spread farther and farther apart. But instead of falling through the air, these cosmic snowflakes are carried apart by the very fabric of space stretching between them. The ones that are farthest away appear to be moving the fastest, not because they're actually moving through space more quickly, but because there's more space between them and us to stretch. This discovery led to one of the most profound realizations in the history of science. The universe has not always been as it is today. If everything is moving apart now, then in the past, everything must have been closer together. Tracing this expansion backward in time, we arrive at a moment roughly 13.8 billion years ago, when all of space was compressed into an infinitely small point, what we now call the Big Bang. But here's where our intuitions often lead us astray. The Big Bang wasn't an explosion that happened somewhere in space, sending matter flying outward into empty regions. The Big Bang was the beginning of space itself. Before that moment, there was no somewhere for an explosion to happen. No empty regions to expand into. Space and time began together, expanding from that initial state into the vast cosmos we observe today. Georges Lemaitre, a Belgian physicist and Catholic priest, was one of the first to fully grasp the implications of this expanding universe. In the quiet of his study, surrounded by equations and star charts, he envisioned what he called the primeval atom, a cosmic egg containing all the matter and energy that would ever exist, compressed into a space smaller than a grain of sand. As this primeval atom began to expand, it didn't grow into pre-existing space. Instead, it created space as it grew. This is perhaps the most difficult concept for us to truly grasp, because our everyday experience tells us that things expand into empty areas. A flower grows in a garden. A city spreads across a landscape. A soap bubble inflates in the air around it. But the universe has no surrounding landscape, no ambient air to expand into. It is all there is, creating its own room to grow. This expansion continues today, roughly 13.8 billion years after it began. The rate of expansion, how fast distant galaxies appear to be moving away from us, is described by what we call Hubble's constant. Current measurements suggest that for every million parsecs of distance, about 326 million light years, space expands at a rate of about 67 kilometers per second. To put this in perspective, imagine two galaxies separated by a distance of about 100 million light years, roughly the distance from our Milky Way to the Virgo cluster of galaxies. The space between them is expanding so that they're moving apart at about 2,000 kilometers per second. That's fast enough to travel from New York to Los Angeles in about 2 seconds, yet on cosmic scales, it's a gentle, stately expansion that has been continuing for billions of years. Now we come to one of the most beautiful and subtle aspects of our cosmic story, the idea of the observable universe. Picture yourself standing on a beach at sunset, looking out over an endless ocean. The horizon forms a perfect circle around you, marking the farthest point you can see. Beyond that horizon, the ocean continues, perhaps forever, but you cannot see it from where you stand. The universe has a similar horizon, though it's created not by the curvature of the Earth, but by the finite speed of light and the finite age of the cosmos. Light travels at about 300,000 kilometers per second, fast enough to circle the Earth more than 7 times in a single second. Yet even at this incredible speed, it takes time to reach us from distant sources. The light from the Sun takes about 8 minutes to reach Earth. The light from the nearest star beyond our solar system, Proxima Centauri, takes more than 4 years. From the centre of our galaxy, light takes about 26,000 years to reach us. And from the most distant galaxies we can observe, light has been travelling for more than 13 billion years, nearly the entire age of the universe. This creates what astronomers call the observable universe, the spherical region around us from which light has had time to reach us since the Big Bang. The edge of this region is not a physical boundary in space, but rather a boundary in time. It's the farthest we can see because it represents the oldest light that could possibly exist. Imagine you're sitting by a campfire on a clear mountain night, and someone begins walking away from you carrying a lantern. At first, you can see them clearly as they move between the trees. As they get farther away, the light becomes dimmer and more distant, but you can still make out its gentle glow. Eventually, they walk so far that their light disappears entirely, not because they've reached some physical barrier, but simply because the light has become too faint to see, or because they've walked behind a hill that blocks your view. The cosmic horizon works similarly, though instead of being limited by the brightness of distant sources, we're limited by time itself. There are surely galaxies beyond our observable universe, possibly an infinite number of them, but their light simply hasn't had time to reach us yet. And because space is expanding, some of that light may never reach us at all. This gives us our first glimpse of how the universe can be infinite yet still have an edge. The observable universe, the part we can actually see and study, is finite. It's a sphere roughly 93 billion light-years in diameter, centered on Earth. But this doesn't mean Earth is at the center of the entire universe. Every point in the universe has its own observable region, its own cosmic horizon, its own sphere of visibility. Picture a vast library with infinitely many floors stretching up and down as far as you could imagine. You're standing in one particular room, and from there, you can see only a certain number of bookshelves in any direction before the view becomes obscured by distance and dim lighting. That visible region is finite and has clear boundaries, even though the library itself might extend forever. Move to a different room and you'll see a different set of bookshelves, though the total extent of your vision remains the same. But there's another type of horizon that makes this story even more intriguing: the event horizon of our expanding universe. Because space is expanding, and because this expansion appears to be accelerating, there are galaxies that we can see today whose light will never reach us in the future. They're not disappearing because they're being destroyed, but because the space between us and them is stretching faster than their light can travel toward us. Imagine trying to walk toward a friend who's standing on a moving walkway that's carrying them away from you. If the walkway moves slowly, you can still catch up by walking fast enough. But if the walkway accelerates and eventually moves faster than you can possibly walk, your friend will forever recede into the distance, even though you're both still perfectly real and present. This creates what cosmologists call the event horizon, the boundary between the region of space from which light can still reach us in the future and the region from which it cannot. Galaxies beyond this horizon are, in a very real sense, leaving our universe, not physically but observationally. They become fundamentally undetectable, as if they exist in a separate reality altogether. To understand how the universe can be infinite yet bounded, we need to explore one of the most profound insights of Einstein's general relativity: the idea that space itself has shape and geometry just like the surface of a sphere or the contours of a landscape. Imagine you're an ant walking on the surface of a perfectly spherical orange. From your ant's perspective, you can walk in any direction, and the surface seems infinite. There's no edge or boundary that stops your journey. You could walk around the entire orange and return to your starting point without ever encountering a wall or falling off an edge. Yet from our perspective, looking at the orange from outside, we can see that the surface is finite. It has a definite area, a specific geometry, and a well-defined shape. This is our first model for how something can be finite yet unbounded. The surface of a sphere is finite in area, but it has no edges or boundaries that an inhabitant could ever encounter. Einstein's great insight was that the three-dimensional space we live in might have similar properties, curved in a higher dimension that we cannot directly perceive. There are three basic ways that space can be shaped, corresponding to three different possible geometries. The first is flat geometry, the familiar Euclidean geometry we learned in school, where parallel lines never meet and the angles of a triangle always add up to 180 degrees. In a flat universe, space extends infinitely in all directions like an endless sheet of paper stretching forever. The second possibility is spherical geometry, like the surface of our orange. In this kind of space, parallel lines eventually converge, just as lines of longitude on Earth meet at the poles. The angles of a triangle add up to more than 180 degrees, and while the space has no boundaries, it is finite in extent. An astronaut travelling in a straight line would eventually return to their starting point, having circumnavigated the entire universe. The third possibility is hyperbolic geometry, which curves in the opposite way. Imagine a saddle shape where parallel lines diverge as they extend outward, and the angles of a triangle add up to less than 100 degrees. In a hyperbolic universe, a base would be infinite, stretching forever in all directions with an ever-increasing rate of expansion. Current observations of the cosmic microwave background, the afterglow of the Big Bang itself, suggest that our universe is very close to being perfectly flat. The geometry is Euclidean to within the limits of our measurement precision. This means that space likely extends infinitely in all directions, filled with an infinite number of galaxies, stars, and worlds beyond our observable horizon. But here's where the story becomes truly remarkable. Even if space is infinite, the observable universe remains finite and bounded. It's as if we're living inside a vast, possibly infinite ocean. But we can see only the water within a certain distance of our position. That visible region has clear boundaries, not walls or barriers, but horizons beyond which we simply cannot see. Picture yourself floating in a perfectly clear mountain lake just as the sun is setting. The water extends in all directions, reflecting the sky so perfectly that you seem to be suspended in space itself. Around you there's a circle of visibility, the region where you can still make out details of the shoreline, see the reflection of clouds, distinguish the gentle ripples on the surface. Beyond that circle, everything fades into a soft blue-grey twilight. Not because the lake ends there, but because distance and the fading light obscure your view. the universe presents us with a similar vista. We float in an ocean of space and time, surrounded by a horizon that marks the limit of our vision. Beyond that horizon, the universe likely continues, perhaps forever, filled with wonders we cannot see and may never be able to observe. This creates a beautiful paradox that touches the very heart of our existence. We are finite beings living in what may be an infinite cosmos, able to observe only a tiny fraction of all that exists. Yet through science and imagination, we can begin to comprehend the whole. It's as if we've been given a single sentence from an infinite book and asked to understand the entire story. As if the question of an infinite yet bounded universe weren't profound enough, modern cosmology has opened the door to an even more extraordinary possibility, that our entire observable universe might be just one region in a vast, possibly infinite multiverse. Imagine walking through a forest where every tree is so enormous that its canopy extends beyond your ability to see. You might spend your entire life exploring the area around a single tree, mapping its roots and branches, studying the ecosystem that has grown up around its base, without ever realizing that you're in a forest containing countless other trees, each supporting its own unique community of life. The idea of the multiverse suggests that what we call the universe, our entire observable cosmos with its billions of galaxies, might be just one tree in an infinite forest of such regions. Each universe within this multiverse could have its own physical laws, its own history, its own fundamental constants that determine how matter and energy behave. This concept arose naturally from our best theories of the very early universe, particularly the idea of cosmic inflation. In the first fraction of a second after the Big Bang, space underwent a period of exponential expansion, growing faster than the speed of light and stretching quantum fluctuations to cosmic scales. These fluctuations became the seeds that eventually grew into galaxies and galaxy clusters. But if inflation happened once, why shouldn't it happen again? And again and again? Picture soap bubbles forming in a bathtub as you add bubble bath to the running water. Each bubble is complete in itself, a perfect sphere with its own surface tension and internal air pressure. Yet new bubbles are constantly forming, and the foam as a whole can grow without limit. In the multiverse theory, our observable universe is like one of these bubbles, a region where inflation ended and matter began to condense into stars and galaxies. But beyond our cosmic horizon, inflation might continue forever, occasionally spawning new universes, each with its own Big Bang, its own physics, its own evolutionary history. The scale of this possibility is breathtaking. If the multiverse exists, then every conceivable variation of physical laws might be realized somewhere. There could be universes where gravity is stronger or weaker, where electrons have different masses, where the speed of light is faster or slower. Most of these universes would be sterile, unable to form stars or planets or any of the complex structures that make life possible. But in the infinite expanse of the multiverse, there would also be countless universes similar to our own, and perhaps some that are even more conducive to the emergence of complexity and consciousness. Think of standing in a vast meadow on a spring morning surrounded by wildflowers of every conceivable colour and pattern. Each flower is unique, shaped by its own genetic history and the particular conditions where it grows. Yet all of them share the same underlying biological principles, the same fundamental chemistry of life. In the cosmic meadow of the multiverse, Each universe might be like one of these flowers, unique in its details, yet part of a larger pattern we're only beginning to glimpse. From this perspective, the question of whether our universe is infinite takes on new meaning. Our observable universe is certainly finite, bounded by horizons we cannot cross. Our entire universe, the full extent of the space that expanded from our particular Big Bang, might be infinite, stretching forever beyond what we can see, and the multiverse itself, if it exists, is almost certainly infinite, containing unlimited numbers of universes like and unlike our own. This creates nested layers of infinity, each more vast than the last. It's like looking into a mirror that reflects other mirrors, creating an endless recession of reflected images, each one containing entire worlds of detail and complexity. Our exploration of cosmic boundaries leads us naturally to consider the nature of time itself, and how temporal limits create some of the most fundamental edges in our universe. While space might extend infinitely in all directions, time has a definite beginning, the moment of the Big Bang, and this temporal boundary creates profound implications for everything we can observe and experience. Imagine you're listening to a piece of music that began 13.8 billion years ago and is still playing today. You can hear only the notes that have had time to reach your ears since the music began. The symphony might be infinitely long, extending forever into the future, but you're limited to hearing only the portion that fits within the span of time since the first note was played. The beginning of the music creates a horizon in time, just as the finite speed of light creates a horizon in space. This temporal horizon manifests itself in one of the most remarkable phenomena in cosmology, the cosmic microwave background radiation. About 380,000 years after the Big Bang, the universe cooled enough for the first atoms to form, allowing light to travel freely through space for the first time. Before this moment, the universe was opaque, filled with a hot plasma that scattered light in all directions, like trying to see through a thick fog. The moment when this fog cleared, when the universe became transparent, created what astronomers call the surface of last scattering. It's the most distant thing we can ever hope to see directly, no matter how powerful our telescopes become. Beyond this surface lies the truly primordial universe, the first few 100,000 years of cosmic history that will forever remain hidden from direct observation. Picture yourself standing at the edge of a vast lake in the early morning, watching mist rise from the water's surface. The mist is so thick that you can see only a certain distance across the lake before everything becomes a uniform grey-white veil. You know the lake extends beyond what you can see, but the mist creates an absolute limit to your vision. The cosmic microwave background is like that mist, a glowing veil that separates the visible universe from the invisible cosmos beyond. But time creates boundaries in other ways as well. Because the universe is expanding, and because this expansion appears to be accelerating, there are events happening right now in distant galaxies that will never be observable from Earth, no matter how long we wait. The light from these events is being carried away from us faster than it can travel toward us, creating what cosmologists call a future visibility horizon. This means that the observable universe is not only finite now, but it will remain finite forever. In fact, as time passes and the expansion of space accelerates, fewer and fewer distant galaxies will remain visible to us. Billions of years in the future, astronomers living in our galaxy will see a much emptier universe than we do today. most of the galaxies we can currently observe will have receded beyond their event horizon, disappearing forever from view. Yet even as distant galaxies fade from sight, new regions of space that were previously beyond our cosmic horizon will come into view. It's as if we're travelling through an infinite landscape where new vistas are constantly appearing ahead of us, while familiar landmarks disappear behind us. The total volume of space we can observe remains roughly constant, but its contents are constantly changing. This creates one of the most poignant aspects of cosmic boundaries. They are not static walls, but dynamic, evolving limits that change with time. The universe we can observe today is different from the universe that was observable yesterday, and it will be different again tomorrow. We exist in a moving bubble of visibility, forever separated from most of the cosmos by horizons we cannot cross. Consider how this affects our understanding of causality, the relationship between cause and effect. Events happening beyond our cosmic horizon cannot affect us, no matter how dramatic or significant they might be. Entire civilizations might rise and fall, stars might explode, galaxies might collide, but if these events occur beyond our event horizon, they remain forever irrelevant to our physical reality. This creates what physicists call causal patches, regions of space-time that can influence each other. Our causal patch is the region of the universe from which signals travelling at the speed of light could have reached us since the Big Bang, and the region to which our signals could travel in the future. It's our cosmic neighbourhood in the deepest sense, the only part of the universe with which we can ever have any causal relationship. As we contemplate the possibility of an infinite universe filled with infinite variations, we inevitably confront questions about our own existence and significance. In an infinite cosmos, what does it mean to be human? What does it mean for Earth to be special or for life to be rare? The anthropic principle suggests that we observe the particular properties of our universe precisely because they are compatible with our existence. In a multiverse containing every possible variation of physical laws, we necessarily find ourselves in one of the universes capable of supporting complex chemistry, stable stars, and the long-term evolution of life. We couldn't observe a sterile universe because we wouldn't exist to do the observing. Imagine walking through an infinite library where every possible book exists, not just every book that has been written, but every book that could ever be written. Most of these books would be nonsense, filled with random letters and meaningless words. Some would contain a few coherent sentences amid the chaos. A very small fraction would be great works of literature, filled with beauty, meaning, and profound insights into the human condition. As conscious beings searching for meaning and beauty, we would naturally gravitate toward the meaningful books. We wouldn't spend our time reading the random gibberish, not because those books don't exist, but because they don't capture our attention or reward our interest. Similarly, in an infinite multiverse, conscious observers like ourselves naturally find themselves in universes capable of supporting consciousness. This perspective suggests that our universe's apparent fine-tuning, the precise balance of physical constants that allows stars to shine, planets to form, and life to evolve, might not be as mysterious as it first appears. In an infinite multiverse, every possible combination of physical laws would be realized somewhere. Most combinations would produce boring, empty spaces, but some small fraction would create universes rich with complexity and wonder. Yet this raises a profound question. If there are infinite universes and infinite variations, are we unique? In an infinite cosmos, would there be other Earths, other versions of human civilization, other individuals exactly like you, having exactly these thoughts at exactly this moment? The mathematics of infinity suggests that the answer might be yes. In an infinite universe with finite variations, even a very large finite number of variations, every possible configuration would be repeated infinitely many times. There would be countless other planets with the same history as Earth, countless other versions of yourself, countless other moments exactly like this one. This idea, sometimes called the principle of mediocrity, suggests that rather than being unique, we are typical, ordinary observers in an ordinary universe that happens to support our kind of complexity. Our Earth, our solar system, our galaxy are not special destinations in a purposeful cosmos, but simply random instances of structures that form naturally when physical laws permit sufficient complexity. Yet there's another way to think about our cosmic significance that finds beauty and meaning even in this vast, potentially infinite arena. Every conscious moment, every act of understanding, every experience of wonder or love or beauty represents something genuinely remarkable, not because it's unique, but because it exists at all. Picture a musician playing a beautiful melody. Even if that same melody has been played countless times before by countless other musicians, each performance has its own value, its own moment of bringing something beautiful into existence. The melody doesn't become less meaningful but because it's been repeated. If anything, its repeated performance across time and space testifies to its enduring power to move and inspire. In an infinite universe, every moment of consciousness, every scientific discovery, every work of art, every act of love and kindness might be repeated infinitely many times. But this doesn't diminish their value, it amplifies it. It suggests that the universe is not just vast and cold and empty, but filled with infinite instances of meaning, beauty, and wonder. Our exploration of cosmic boundaries thus leads us to a profound realization. We are simultaneously infinitesimal and cosmically significant. Infinitesimal because we exist in a tiny corner of what might be an infinite cosmos, observing only a minuscule fraction of all that exists. Cosmically significant because our consciousness allows us to contemplate the whole, to find meaning and beauty in our small piece of the larger story, and to participate in the universe's capacity for self-understanding. As our journey through the landscape of cosmic boundaries draws toward its gentle conclusion, we find ourselves in a place of profound wonder. We have explored horizons that mark the limits of observation, boundaries that exist in time as well as space, and the possibility that our entire universe is just one note in an infinite cosmic symphony. These boundaries, rather than confining us, have revealed the extraordinary richness of our cosmic situation. We are like explorers who set out to map a small island and discovered instead that we live on the shore of an infinite ocean. Every boundary we encounter, the particle horizon that limits our vision, the event horizon that determines our future, the causal boundaries that define our cosmic neighborhood, opens up new depths of mystery and beauty. Consider the cosmic microwave background, that gentle afterglow of creation that reaches us from the edge of the visible universe. This ancient light, stretched and cooled by billions of years of cosmic expansion, carries within it the imprint of quantum fluctuations that existed when the universe was smaller than an atom. In studying this light, We are quite literally looking back in time to witness the birth of structure in the cosmos. The temperature variations in this primordial light are extraordinarily small, differences of only a few millionths of a degree. Yet from these tiny seeds grew all the magnificent structures we see today. Galaxies swirling through space like cosmic hurricanes, stars burning in the darkness like distant campfires, planets where chemistry became complex enough to support the emergence of life and consciousness. There's something deeply poetic about the fact that the farthest things we can see are also the oldest things we can observe. The edge of the observable universe is simultaneously a boundary in space and a window into time. The most distant galaxies appear to us as they were when the universe was young, their light carrying messages from an epoch when the first stars were just beginning to illuminate the cosmic dark. This temporal aspect of cosmic boundaries creates what we might call the universe's memory. Every point in space contains light from every epoch of cosmic history, layer upon layer of information about how the universe has evolved and changed. We are surrounded by this invisible archive, a library of light that preserves the story of everything that has ever happened in the observable cosmos. The boundaries of our observable universe are not walls that confine us, but horizons that invite exploration. They represent the current limits of our knowledge and observation, but they also point toward the vast unknown that lies beyond. Every new telescope we build, every new observational technique we develop, allows us to push slightly closer to these fundamental limits. Yet there will always be horizons beyond our reach, mysteries that remain forever hidden from direct observation. The universe before the cosmic microwave background became transparent. The regions beyond our event horizon, the other universes that might exist in the multiverse, these remain accessible only through indirect inference, mathematical modelling, and the careful construction of theoretical frameworks. This tension between the known and the unknowable is one of the most beautiful aspects of our cosmic situation. We are finite beings capable of contemplating infinity, temporary structures capable of understanding eternity, local observers capable of grasping universal principles. Our boundaries do not diminish us, they define the stage on which the drama of scientific discovery unfolds. In contemplating these cosmic boundaries, we also confront the boundaries of our own existence. Each of us lives within our own personal event horizon, the limit of what we can experience, understand, and influence during our brief time as conscious beings. Yet through science and imagination, we can transcend these personal limitations and participate in humanity's collective effort to understand the cosmos. The story of cosmic boundaries is ultimately a story about perspective and scale. From our vantage point on a small planet orbiting an ordinary star in an unremarkable galaxy, we have learned to think about the universe as a whole. We have developed the conceptual tools to contemplate infinity and the observational techniques to study the most distant and ancient objects in the cosmos. This represents one of the most remarkable achievements in the history of thought, the ability to transcend our local perspective and adopt what cosmologists call the cosmological principle, the idea that the universe looks roughly the same from any vantage point. We have learned to see ourselves not as the center of creation, but as observers participating in a vast, dynamic, evolving cosmos that extends far beyond anything we can directly experience. As we float here in our imagination, suspended in the gentle darkness between the stars, we can feel the profound peace that comes from contemplating our place in the cosmic order. The universe, with all its mysteries and boundaries, has revealed itself to be not a cold, empty void, but a tapestry of extraordinary richness and beauty. The boundaries we have explored tonight are not barriers, but invitations to wonder. They remind us that existence itself is a kind of miracle, that out of the quantum foam of the very early universe, complexity and beauty and consciousness have emerged. Think about the extraordinary chain of events that had to unfold for this moment to exist. The precise balance of forces that allowed the first atoms to form, the gravitational dance that gathered those atoms into the first stars, the nuclear furnaces that forged the heavier elements essential for planets and life, the delicate conditions that allowed chemistry to become biology on at least one small world orbiting one ordinary star. In an infinite universe, this chain of events has perhaps played out countless times in countless variations, yet this knowledge doesn't diminish the wonder of our particular instance. If anything, it amplifies it. We are part of a cosmic symphony in which themes of complexity and consciousness arise again and again, each performance unique, each moment of awareness a note in an infinite composition. The boundaries of the observable universe create a kind of cosmic intimacy. Rather than being lost in infinite space, we find ourselves in a comprehensible region, vast beyond imagination, yet finite enough to study and contemplate. Our cosmic horizon creates a sense of home on the largest possible scale, a boundary that defines our cosmic neighbourhood and gives structure to our place in the larger whole. There's something deeply comforting about the realization that we share this cosmic neighbourhood with billions of galaxies, each containing billions of stars, many of which likely have planets where the chemistry of life might unfold in ways both familiar and utterly alien. We are not alone in our corner of the infinite. We are part of a vast community of matter and energy, all of it bound together by the same physical laws, all of it participating in the same cosmic evolution. The gentle expansion of space carrying distant galaxies ever farther from our view creates a kind of cosmic twilight, a gradual fading of the observable universe that will continue for billions of years to come. Yet even as distant lights disappear beyond our horizon, new regions of space come into view, bringing fresh wonders and new opportunities for discovery. This ongoing revelation reminds us that the universe is not a static picture to be examined, but a living, evolving story in which we are both observers and participants. Every moment brings new light from distant realms, new information about the cosmic past, new insights into the nature of space and time and matter. As conscious beings capable of contemplating these vast scales and deep mysteries, we represent something truly remarkable in the cosmic story. We are the universe becoming aware of itself, matter and energy, organized in such a way that it can contemplate its own existence, wonder about its own nature, and find beauty in its own vast complexity. And so we come to the end of our gentle journey through the cosmos, though in truth, such journeys never really end. They simply pause, like a beautiful piece of music between movements, waiting to be resumed in dreams and quiet moments of contemplation. Tonight, we have explored one of the most profound questions in all of science. Can the universe be infinite and still have an edge? We have discovered that the answer is not just yes, but beautifully, elegantly, necessarily yes. The universe reveals itself to be far more subtle and wonderful than our everyday experience might suggest, a place where infinity and boundaries coexist, where the finite and the infinite dance together in perfect harmony. Our observable universe is finite, bounded by horizons of light and time, creating a cosmic home of comprehensible scale within what may be an infinite larger reality. These boundaries do not confine us but define us, creating the stage on which the drama of cosmic evolution unfolds, the frame within which complexity and consciousness have emerged from simplicity and silence. As you settle into sleep tonight, imagine yourself once more floating gently in that vast cosmic ocean, surrounded by the soft light of distant stars. Feel the slow, steady expansion of space, carrying you peacefully through the darkness. Part of a universal motion that has continued for nearly 14 billion years. Know that you are simultaneously infinitesimal and infinite, a brief, beautiful note in a cosmic symphony that may play forever. The universe, with all its mysteries and boundaries, has given rise to this moment. Your consciousness contemplating its own cosmic home, finding meaning and beauty in the vast scales of space and time, participating in the extraordinary fact that matter can wake up and wonder about itself. Rest now in this knowledge, letting the gentle rhythm of cosmic expansion carry you into dreams where boundaries dissolve and infinity becomes as natural as breathing. The universe continues its patient evolution around you, creating new possibilities with each passing moment, weaving new patterns of complexity and beauty into the endless tapestry of existence. Sweet dreams, fellow cosmic voyager. The infinite universe, with all its edges and horizons, holds you gently in its vast embrace and will be waiting to share new wonders when you wake.